And then we didn't cover the sigma stuff, so you don't have to do those. Okay, we're moving on. This is going to be a lot of content, so prepare the brain. Massage the brain.
Winky, winky.
All right. Epic gamer moments forthcoming.
Is that still a thing?
Twitch.com. Poggers.
Because I didn't even know when it was a thing, so like, is it continued? I don't know.
Okay.
Okay. I'm very out of the.
Let's start with something. One of the biggest things in all of calculus. Okay. Hannah, put that toy away. Thanks. Is there a function that's equal to its own derivative? There's a question. This is a big question to ask. Is there a function y where y prime is equal to y?
You said.
Yeah.
Told us numerous times.
Yes. They told you. Do you remember the answer?
You said that.
E to the x power is the answer. Now, I'd like to give you maybe some intuition behind that, which is, well, if you look at this and say, well, a function whose basically his y values are equal to his slopes. So basically, as the y values get bigger, the slopes have to get bigger, and as the y values get smaller, the slopes have to get smaller. And so if you look at it, if you think about that, you might start thinking about like, oh well, I guess an exponential growth graph would do that. Like, see over here, big y value, big slope. Not so big y value, not so big slope. But you can see the y values are always positive, and so are the slope values. Right?
Mm-hmm.
Making sense?
Yeah.
Yes, listen.
Would that be the same for y equals 2 to the x?
Not quite. So that's a good question. So like you might start with this shape and then be like, well, maybe it's like, do you think it's y equals 2 to the x? In a class called like in a higher level calculus or math class, like an analysis class, you can get into more like the nitty gritty details of like how to arrive at this. But the easiest is to say by definition, you can kind of test that this function, if you analyze, like say pick a point on the slope, for example, say we know that when you plug in 3, you get 8, right? You could analyze using the limit definition of the derivative and figure out, the slope's actually, in this case, a little bit, I think, smaller than the y value. You can figure out that this slope is actually not quite 8. And then you go, okay, I guess that this number has to be bigger then. You need a steeper growth curve, and then blah, 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 you arrive at this.
E is the answer, David.
Yeah. In fact, this is actually, this is one of the definitions of E. If you ask the question, what is E? E is the number such that the exponential growth curve with this number as the base is equal to its own derivative. So that's one of the most powerful definitions of E you can start off with. Okay, anyway. Lit indeed. So the first fact and logic that we know is, this is a big fact, the derivative of e to the x is equal to e to the x. Ooh, big fact there. So now we know a rule called the chain rule. That's really famous. It comes up a ton when you're learning calculus and derivatives. What's the derivative of e to the u then? It's $1 million question. It's going to be e to the u, except what do we always tack on when you do the chain rule? Tack on to u prime. It's as simple as that. Chain rule lives.
Chain rule lives.
Chain rule is the chain rule. It doesn't just it applies to every function out there. Okay, so any function that you know the derivative of, you then automatically know what's the derivative of that function if there's a function inside the function. Okay. So, what's the answer to the first question on our assignment then?
5.
Yeah, the derivative is, so e to the 5x, what's our u? Well, our u is 5x. This means our u prime would be 5. Sorry, the equal sign is very ratchet. Sorry about that. U prime would be 5, so the chain rule tells us that the derivative of e to the 5x would be 5 times e to the 5x. Easy peasy, right?
Easy peasy, McSqueezy.
McSqueezy?
No, it's actually, I guess there's a lot to cover, but that's the first thing. Cool beans?
Cool beanies.
All right, let's look at the next one. What's the derivative of 4 to the x? Ooh, scary. Scary. By the way, if you're wondering, we're starting on 5.2 because I have a 5.1 that's just a review of exponents and logs and trig, but for the sake of time, I'll try to review it as we go. Okay, so 4 to the x. Who thinks, does anyone have an idea of what just the overall strategy might be if I was interested in knowing the derivative of 4 to the x?
Try to figure out how you make it e to the x.
Yeah, I'm going to look over here and be like, well, I have this really nice result. Can I make it look like that? And the trick here is to know that, well, 4 is the same as e to what power?
Oh, God.
Where?
The natural log.
The natural log of
Is it?
4.
Oh, yeah.
Oh.
First. This is where. Oh.
Big fact. Mimes, no cap.
Oh.
Communicate with the zoomies, Jesse.
That looks like
Speaking your language here, Jesse.
Oh, see, I thought that the drawing was of this.
Yeah.
No, I can see that.
It's a hat.
Yeah.
Everyone's a critic. Everyone's a critic. Okay.
No.
Don't you
So
like
you
that?
have to add a little tiny dot on the top. You know the
There's a
little,
picture of Naruto.
you know the little tiny dot on the top? That's what you need. Okay. I thought it
Lateral
was
nod.
that is a great picture.
That's
Yes.
Can I
fantastic.
take a picture of that one?
in middle school.
Okay. Do we understand this? If you don't understand it, let me try to explain it to you then. So if you say, what does the number natural log of 4 mean? Well, let's see. The natural log of 4 is equal to some number, right?
One could assume.
Well, what this says is that this is the number so that e raised to that power would give you 4. Right? It's a little review of what a logarithm is, right?
Yeah.
A logarithm is a different way of writing an exponential statement. Okay, so if this is a number, it's a special number so that e raised to that number is equal to 4, what happens if I raise e up to that number? I better get 4, otherwise nothing I said made sense.
I better.
Yes? Make sense?
Yep, thank you, Winky.
I'll give you one more brief explanation of it, just for the sake of review here. So this is a really central concept. The natural log of a is equal to b is the same thing as writing e to the b power equals a. Okay? So look at this. So if I write e to the natural log of 4 equals 4, I could rearrange that. E to the, so this is my b, and this is my a, right? E to the b equals a can get written as the natural log of a equals b. Is that a true statement?
Yeah.
Yeah, so that's a true statement. So there you go. Is it making any sense?
Yes.
That's
Okay.
proof.
Well, can you do a quick review on logarithms just by
I just did.
themselves?
I just did.
No, that wasn't.
Just like logs, not natural
No.
logs.
Okay.
Once I'll do that.
And we'll draw
Log base 2 of 8 is equal to 3 because 2 to the 3 power is equal to
okay. There we go. There we go. There we go.
Natural log is just log base e, right? Natural log is just log base e. Don't be scared of it. Okay. So, we okay? All right.
So
So
far.
what I'm going to do here then is say, well, this derivative is, so this 4 is really e to the natural log of 4 power, and that's raised up to the x power. So what are those exponents going to do? They're going to multiply, so. Now, what was the derivative of e to the 5x?
That was so funny.
5e to the 5x. So this is going to be, wait a minute, what, that scares me. What is that?
One.
That's just a constant, just a number, right? So this is like saying e to the 5x, except instead of 5, it's a little bit scarier of a number, right?
Line.
So it's going to be that number,
Line.
right, times e to that number times x. But wait a second. What's that?
Ooh, it's too much thinking.
What's e to the natural log of 4 power? It's 4.
Oh.
You can use that. Look, see? Do you see?
Do you
Do
see?
you see?
Hold on, stop, stop,
Winky, winky.
stop. You stop.
Just for you, Jesse. Okay. So wait a second. Now, is there anything special about the number 4 that made that work out? No, that could have been a 7, a 19. It doesn't matter. It would have worked out the exact same way. So I could make myself a note that says the derivative. This one sucks. Okay, that any number, let's call it a to the x power is just going to be the natural log of that thing times the thing I started with, a to the x. Cool beanies?
Cool beans.
You feel fine about that?
Yep, my Smith thread is blowing up. I have like a notification every second.
That was violent.
Yeah,
Fine.
yeah.
That's a ball.
Was the violence made?
Yeah, ball.
Was that to get rid of?
Ball. All right. Do you guys feel okay about that? Wait a
Yes.
second. Oh, there's this thing called the chain rule. So could I generalize that and say, well, what if instead of a to the x power, what if I had, I don't know, maybe you like it better if there's just a number in there. Like, say I said, I don't know, 6 to the u power.
Okay.
So if I had 6 to the u power, I'd have the natural log of
Oh, 6
6
times.
times,
6 to the power.
and then what do we always tack on when we do the chain rule? Yeah. How do we feel about that? Is that
Good. Can we change? Can I make the 6?
you can make it an A if that makes you feel better. Make it a B, not a C though, not a C.
Okay,
No, it could be.
but I'd rather make it a J. Can it be a K?
Sure.
It's a J now.
Okay, J's. Well,
J is my name, J Hall, so leave me alone. So it's yours too. Yeah. So shush.
Shush.
J is
Anyway.
the best letter.
It's a pretty good letter.
The
Yeah.
unfortunate thing is I just
Trenton,
wrote
you
a
would be
6,
the one
and it was
to-
a
At least
really
it's not the
Really?
letter O. I
Six.
hate the letter O.
You would enjoy this conversation.
So Michael McKay and I have decided on this quest to get rid of Q. Q's.
Q?
Replace it with K.
The letter
And
Q.
replace it with K.
bro, if that makes you
I
mad,
like the letter Q.
when you do
That
really
would be-
exotic.
Or
vector calculus, you'll do a lot of I's and J's. You'll do I, J, K. Doing like some huge problem with lots of I's and J's next to each other can be very
Nice.
annoying. And then when you do some like number 3 stuff, they'll do N's and M's.
Yes.
But then when you talk about it, it's very annoying because you go, oh, the GCF of N and M, then the M does this and then N. But if N and M do this, why do they pick N and M? They sound the same.
M&M's?
They sound the same. Okay,
Winky, winky.
let's use that
So I'm
on
sure the candy M&Ms are really disturbing to you.
this dude. What's the derivative of 2 to the root x power? Well, hopefully that one I just showed you makes sense to you. This is a chain rule.
Mm-hmm.
So this is 2 to the u. So remember, 2 to the u is going to turn into u prime times the natural log of 2 times 2 to the u. Are we cool beans with that? Go okay with that? Sure? Okay. What's my u? The square root of x. So what's u prime? 1 over 2 root x. Very good. So this is going to read 1 over 2 root x times the natural log of 2 times 2 to the root x. Easy peasy.
Lemon squeezy.
That's it. That's all there is to it.
Wow.
I love it.
I don't.
Well, Abby, do you love anything in math?
Yes.
Yes.
It was
So-
exponential growth.
Or
I was good at that.
we put E prime
Yeah, that's not my favorite.
We did, sort of, because what's
I know.
u?
That's not my least.
X
Okay, so what's u prime?
1. Ah.
Okay, let's look at c. C is very interesting. If you really thinky about it, it's very
Thinky, so
interesting.
banky. Thinky?
What rule do you think we're going to have to use on C?
Our thinking we.
The thinky rule, the product rule.
Thank you.
Okay, product rule. So don't forget the product rule. And so this whole thing here, guys, is going to be one, learning all these facts like the derivative of e to the x is e to the x. And then it's also going to, so then we're going to also do sine, cosine, tangent, all that stuff.
Oh.
Life is pain, I know.
It is.
Born to suffer. But then it's going to be a review of product rule, quotient rule, chain rule, and then all the other stuff. Equations of tangent lines, all the stuff we learned about derivatives in the first place. So hopefully that'll be a good review for you.
Woo!
Okay.
I'm the only person who will ever cheer about that one.
I
You are
appreciate
correct.
it.
Well, that's good.
My appreciation for you is over 9,000. It's my meme of the day. It's just so meaningful.
I like it.
Now,
That's
J-House,
So
can you tell me
meaningful.
where that comes from?
That's
Tell
good.
me the name of where
I
that
like
comes
that.
from.
From Naruto.
I did.
No.
Yeah. So
Say it again. Isn't that all? It's so meaningful.
meaningful amount. That's a good
Come
one.
on, Jay Hall, you know, I know. And
What?
I don't even watch it.
You
What
know
show is
what
on?
that show is. You got it.
It's the show where the Attack on Cowboy Bebop or something. Where the
No.
You.
Goku fights Naruto for the crystal skull. Yeah. And then Black Butler comes in and
No.
Anyway.
I never want to give a music Black Butler ever again.
Okay.
That was awesome.
Remember, guys, the derivative. So if you're doing a question like this, and let's say you go, I know it's a product of two functions. I remember there's some kind of product rule. You could look it up and say, okay, f times g would turn into f prime g plus g prime f. So if you feel like you're more comfortable listing out the info, fine. You could say, okay, f is x, so my f prime would be 1. My g is this e to the x, so my g prime is also e to the x. And so when I write out my product rule, it's going to be f prime times g plus g prime times f. And then we certainly can simplify that. Now, I don't know, do you see why that is kind of an interesting function?
Yes.
Or an interesting derivative, because then you might go, well, wait a second, that means taking the derivative of this function is equivalent to adding e to the x onto the function. So if you took the 1,000th derivative, if you think about that, you'd be adding
To the X.
that e to the x on 1,000 times. It's kind of weird.
Lamau.
Lamau indeed.
wrecked.
Lamau indeed. Let's go down to g.
So would it just be 1,000 e to the x plus x e to the x?
I think so.
Okay, this group chat needs to shush.
Then turn it
I
off.
will.
Good.
That feel when you get left unread in the group chat. Am I right, fellow Zoomies?
Yes.
That's so relatable.
That's never happened to me.
I was stopped. I had to train for
That's not a
30
problem.
minutes after. Yes.
Oh my god.
And I messaged a group chat. And
Oh god, wait.
Did you say PLS respond uwu?
I said, train. I didn't realize it was train. All I know is train.
You put this analogy in there?
Yes, I was stuck by a train.
Okay.
The 50 Shades of Grey?
Next one. I'm gonna erase that. Okay, I'm gonna erase that. Look at G. What do we have to use for G?
But then they all.
How do you? Trey got it, but we all understand that when we have a quotient of two functions, we have to use a quotient rule. So you have an f over a g. So the quotient rule says the derivative of this is f prime g. All over g squared. Yep. So there's our quotient rule. So this guy. Do you guys? Is it helpful to list them out or?
Yes.
Yeah.
Okay. So the way I've written this, then I have my f. My f is e to the x. So f prime is
E to the
e to the x. My g is x. So my g prime is 1. And then let's plug them into the chain or the quotient rule. So you'd have f prime times g minus g prime times f all over g squared. We could simplify that. Probably seems nicest to write it like this. There we go. So this one, I mean, kind of weird. Like the last one we did was saying like that funky function, taking its derivative was equivalent to adding an e to the x onto it. This one, taking its derivative is equivalent to taking away an e to the x and then dividing everything by the square of x. So that's a little weird. Okay, so sure. I mean, so f is just, well, I'll just give you a hint here. You have 5 times e to the u on question f. What's the derivative of 5 e to the u?
It's u prime times 5 e to the u.
U prime times 5 e to the u, right? Remember, having a multiplicative constant, that plays very nicely with derivatives, right? The derivative of 7x squared is just 7 times the derivative of x squared. So same thing applies here. The derivative of 5 e to the u is just 5 times the derivative of e to the u. Okay,
Yeah.
George, put that away.
The third plus 3 is 3. Integral.
All right, do we feel okay?
No. That's the integral. The derivative of 3 is just 0.
Let's see it.
Yeah, we're in an integral brain.
We're going to do that next. Well, first we're going to learn all the derivatives. We're going to learn and practice all the derivatives we got to know, and then we're going to the next problem set will be, well, let's integrate. It's actually very easy to integrate. You just go backward. Spoiler alert, guess what the integral of e to the x is, Aaron? Plus c. Oh, excuse me. Wow. All right, I want to skip to 3 now, boys. We're going to...
Did you say boys? Because that's the best thing ever, and I'm not going to use boys. Boys. But it has to be like G-O-I. Boys.
Yeah. All right.
Or like G-O-E-E-S. Boys. G-O-Y-E-E-S. What are we going for? 3?
We'll see if any of you guys are trivia champions. Does anyone remember? I might have mentioned this once. What's the derivative of the natural log function?
Is it?
Savage.
Dude, what is it? Dylan.
Spoiler alert. Okay, so this question says, this one has a very interesting answer. So it says, well, first we got to figure it out. So it says, use implicit differentiation to find out what the derivative of that function is. Okay. By the way, if you graph this function, it's a little bit of review for you. Do you remember what that graph looks like?
It's like an
It's like
inverted.
we up from the
Yeah.
bottom. Yeah.
There's exponential growth. This is the inverse of that. So
Approaching.
We.
Yeah.
Yep.
So think about these slopes. So this is my y graph. So if I just maybe graph the derivative over here, it gives us a big clue as to what it looks like. What kind of slopes do we have for small x values?
Very, very.
Large.
Those are positive slopes,
Yeah.
right? The function's increasing very rapidly for small x values. So if x was like 0.1, 0.01, we'd expect a very large derivative, right? See what I'm talking about?
Yep.
So start off with some really big values, big positive values. And then what happens to these derivatives as you move along the curve?
Zero.
They seem to be approaching zero, right? They seem to be getting less steep, right? But staying positive, right? So what that tells me is that my derivative should be a function like this. Okay? Does that all make sense?
Yeah.
All right, so let's do the calculation then. So it says use implicit differentiation. So the trick is I'm going to rewrite this. So if I try to take the derivative right now, that's circular. I go, I wonder what the derivative of natural log of x is. Take the derivative, I'm now posed with the same question. So I have to then use some tricks. I can rearrange this to say e to the y power equals x. Do we feel okay about that? Make sense? Okay. Now let's take the derivative. This is called implicit differentiation. Remember doing these where you had like y's, you had things like y squared and y cubed. What's the derivative of e to the y? Okay, hold on. We know the derivative.
Sorry. We know the derivative of x, so it's going to be
Y prime.
y prime.
Yeah, so we know this is true. Is a y any different than a u? No, y is a function. So this is going to be y prime times e to the y. Does that make sense? I'm taking the derivative of both sides. What's the derivative of x? 1. All right. What am I trying to find in this thing?
That's not confused. So when we usually take the derivatives, don't we usually do it in terms of either x or 1?
Yeah, so what I'm
So it's
doing.
y prime, so you're doing it in terms of x.
Yes, so that's a great point. I want to be really complete with what we're doing. I'm taking the derivative with respect to x. Every time we did implicit differentiation, we always were doing it with respect to x, or maybe t sometimes, if there was like a particle moving along the curve. This is good to show. People typically don't show this, but you can definitely clarifies what you're doing. Hey, I'm taking the derivative of both sides of my equation. So getting back to the core of all algebra, right? You can do whatever you want to both sides as long as you're consistent. So y prime times e to the y is equal to 1. Cool beans? No confusion? What are we looking for? What's the thing we're searching for here?
Y prime.
This guy, right? That's what I'm trying to figure out, is what is y prime. So let's solve for it. Make sense?
Mm-hmm.
And then, do you see?
It's 1 over.
You're like, wait, e to the y is x, right?
Mm-hmm.
Okay, so therefore, y prime is equal to 1 over x. Although, if you want to be
But you can't.
technical, you'd go, well, wait a second.
You
This function doesn't even have a derivative for negative x values. So if I want to be really precise, I'd say, well, it's the 1 over x function that only accepts positive numbers.
Lit.
Lit indeed.
Y Oh.
That's a mood.
Y equals x.
The more complete answer to that question is e to the y equals x because of the original definition of the function. Y equals log of x, so that's the same as saying e to the y equals x.
Yeah.
All right, so how difficult is it going to be to do? Let's put it down here. This is maybe a hint of how difficult it is. No. It's very simple. The derivative of natural log of u. Chain rule. If the derivative, so reading of the chain rule, if we know that the derivative of the natural log of x is 1 over x, that therefore the derivative of natural log of u is 1 over u, and then what do we always tack onto this? U prime.
Do you need the caveat of that it has to be greater than 0?
And maybe, well, sort of, kind of. We usually don't nitpick too much. It kind of depends on the context, I guess.
Will the test make it?
No, they're not going to be like this.
What?
Okay, does that make sense?
Yeah.
Now you could write this as u prime over u. I like to write it this way just because, well, I like to write it both ways, but this way, this is a nice way of showing how the chain rule is just being applied simply here, right? Same exact derivative, you just tack on the u prime. That's all you do. All right. One last thing to cover. I guess you guys haven't been tortured enough. You need a little bit more. Just a little. Right, Jesse? What was that? Were you shaking your head or were you nodding your head? You were just like,
Both.
Yes.
all right. Look at 4.
That was I love calculus, but I also want to be done with high school.
Big mood, no cap.
That is a partial
Okay,
mood.
but there's gotta be something you enjoy in school that you're like, I really like this, but I
Well,
wow, I don't
Watching
know.
Naruto tell Goku that it's over 9,000, am I right?
On repeat.
That's pretty good. That's pretty relatable, right, Trenton?
His name is Vegeta.
What kind of name is that?
They named the rest of their villains in this new series after vegetables.
Wait, I thought his name was like Frieza.
No, that's on the villains. Frieza.
Is that the one that would go,
That's the purple one.
I haven't even reached my final form?
No, that's the purple lizard. Yeah, everybody's named after a vegetable.
Specifically the same.
Okay.
Wait, what's
In the
the-
book or another name for cereal.
Yeah.
My villain name would be.
Arrogance. I gotta show you something.
I gave up.
Change of base
after
formula.
school.
Listen up. Listen up.
We're learning.
So this is ancient knowledge here. So it's going to be really important for solving 4. So there's a famous little change of base formula. So you may or may not remember this from last year. It's kind of I spent like 10 minutes on it. So suppose I wanted to know something like, what's log base 3 of I don't know, 10. Well, with modern calculators, you can just type this directly in, log base 3 of 10. So, but in the old days when your calculator only had, say, natural log on it, what?
The olden days.
The olden days.
Back in the day.
Um,
Oh my gosh.
Even like a TI-83, like doesn't have you can't type in log base 3 of 10. So what did they do back then? What they would do is they would say, well, let's see, this equals something.
I'll tell you later.
So 3 to that power is equal to 10. All right. And then what I'd say is I'm going to take the natural log of both sides. That's legit, right? You know how to do that.
Yeah.
You can do whatever I want to both sides of the equation as long as I do it to both sides of the equation.
You bet
And then
you
who remembers what can happen to this exponent?
In the front.
We can move out front.
Yeah.
It can live here. And then I could divide both sides. So I'd have the thing I'm looking for, question mark, times the natural log of 3 equals the natural log of 10. And so I guess the thing I was looking for is the natural log of 10 over the natural log of 3. So what they would do,
Right.
when your calculator only had one type of log it could do, is you'd actually do this. Do you feel okay about that?
Yeah.
Now, of course, my choice of 10 and 3 was arbitrary. You can do this for anything. So, so for 4 on our assignment, when you're doing, what's the, no, losing my mind. I'll just write y. Log base 2 of x, so look at that. Log base 3 of 10 is equivalent to natural log of 10 over natural log of 3. So before I take the derivative, how am I going to write this? Very good. Natural log of x over the natural log of 2. And if it makes me feel better, I'm going to say, well, wait a second. That's just the same as saying, what is that? What is that? Scary. It scares me. Simple answer. It's a number.
Yeah.
It's a number. Is this really any different than a 3 or a 7, right? Like, it's just a number, right? So, see what I'm getting at?
Mm-hmm.
Watch how easy this is going to be then. So you're telling me that the log base 2 of x is really just a multiple of natural log of x.
Oh,
So what's the derivative going to be? I'll ask you a simpler question.
oh, the derivative.
What's the derivative? Well, hold on. Let me just. What's the derivative of 7 times the log of x? What would you get there? Gosh, I failed you all. I'm so
No,
sorry.
no.
7 times 1 over x.
Yes, sorry. 7 times 1 over x. I just couldn't remember if it was
Pretty accurate.
what it was. 1 over
Right?
X. Yes, yes.
I remember.
What's the derivative of log of x? 1
Right.
over x. So the derivative of 7 times log of x is 7 times bigger than that. Okay?
Yeah.
That's true for every function in the whole world. If you know the derivative, then you also know the derivative of any number times that thing. Okay?
Yes, yes.
So this thing is just a number. So my derivative is that number times 1 over x. All right? And then Jesse, if you wanted to be like, well, technically x can only be positive if you want to be really precise, then yes, you could add that. Add that
Well,
as
we know that I always want to be super precise.
true. Okay. And then my final remark would be, what if it's a chain rule? The last thing would be, well, what if I had, well, firstly, log base a of x,
It's unfortunate.
log base a of x, then, so log base 2 of x turns into this constant times 1 over x. So log base anything of x would be
1 over line of anything.
1 over natural log of a times 1 over x. Yeah?
Yeah.
The derivative of the natural log of x is 1 over x.
We did that in.
That was number 3. And then so the derivative of log base a of u would just be the exact same thing, but what else is going to have attached? There's going to be u prime attached. Oh, sorry, that's not an x, is it? It's 1 over u.
Oh, you almost killed us.
Almost killed you. So oh, that makes sense. The derivative of, remember the derivative of log of u is u prime times 1 over u. So the derivative of log base a of u is the same thing. It's u prime times 1 over u, but it has this extra multiplier on it.
Yeah.
So there you go. That covers all.
Woohoo.